Hello, everybody. I'm Lisa Levin, and I'm pleased to represent the Deep Ocean Observing Strategy today. This is a program within GOOSE that envisions a globally integrated network of systems that observes the deep ocean effectively in support of science, policy, and planning for sustainable oceans. And for DEUCE, our concept of what is deep, it's a little bit unorthodox, but we consider processes and mechanisms below the photic zone that are greater than 200 meters that influence deeper depths. Although many within DEUCE believe the focus of observing must be below 2,000 meters. If you'd like to learn more about DEUCE, I refer you to our Science and Implementation Guide, which can be found online. And today I'd like to summarize a little bit about DEUCE and focus mainly on how we can interact with ocean sites. And I'd like to start simply by reviewing the DEUCE terms of reference. These are to build understanding of what's most important to observe in the deep sea, our essential ocean variables. DEUCE intends to provide a hub for integration opportunities and to coordinate deep sea observing, to develop deep sea observing requirements, to build readiness and observing technology and techniques, to foster availability, discoverability, and usability of deep ocean data, and to create a common community science implementation plan for deep ocean observing. We held a scoping meeting at Scripps at the end of 2016, and from this emerged a series of science questions that require deep observing. In the physics realm, these are to understand global deep and bottom water formation rates while assessing global heat, salt, and freshwater budget dynamics. In the biogeochemistry realm, these are to document deep ocean tracer transport and ventilation processes and assess their impact on ocean biogeochemical processes at the seafloor and in the water column. In the biology realm, these are to understand marine deep sea biodiversity and ecosystem services in light of human-induced and natural changes. And we've added an additional question that deals with responses to climate change, recognizing that nature-based and any proposed geoengineering technologies will require firm scientific grounding in terms of their feasibility and impacts on the deep ocean. In the last few years, DEUCE has evolved a focus on integrating biology into what is effectively sort of a physics and chemistry dominated field of observing, and also to integrate modeling into both the design of observing programs, I should say modeling needs into the design of observing programs, and to facilitate use of deep sea data by modelers. We also hope to expand engagement in deep observing among members of to include members of the exploration community and to include extractive industries which are emerging and developing in the deep sea. This slide shows sort of a conceptual diagram of what we hope to do implementing DEUCE going forward. And really I show it to illustrate the communities of scientists and data providers that we hope to bring together. You can see that Ocean Sites features prominently among the observing networks we hope to link. But there's also many in the data community, a large modeling community, and many different projects and stakeholders that focus on the deep sea. And we hope to bring all of these folks together. For the remainder of the presentation, I'd like to talk about DEUCE and its possible relationship to ocean sites with respect to maturing, advancing, and implementing EOVs, our demonstration projects, and data integration. DEUCE has 3 panels that work on identifying essential ocean variables that are of greatest significance for the deep sea, and also looking at the GOOSE EOVs with respect to specific to specifications and specific needs. The three panels have added a series of recommended a series of added essential ocean variables shown down here in green for physics, biogeochemistry, and biology. The BioEco GOOSE panel also works very closely with the biology GOOSE panel on developing now the microbe and invertebrate EOVs. I'd like to go through each of these with some recommendations for how we could work with ocean sites. We recognize that deep ocean phenomena is a highly multidisciplinary, I should say that understanding deep ocean phenomena requires multidisciplinary observations, and that by adding observing capacities to ocean sites, we can help really advance the science. And I'd like to now go through with respect to physics, biogeochemistry, and biology, how we might do that. There are three recommended deep physics EOVs that ocean sites could help advance. Ocean bottom pressure is the most mature of these. It's been accepted by GOOSE as an emerging EOV, and measuring ocean bottom pressure will help advance understanding of sea level changes, ocean circulation, gravitational tides, internal waves, tsunamis, infragravity waves, storm surge, and more. And we hope that ocean sites can consider adopting measurement of ocean bottom pressure. Ocean mixing is another deep EOV. It's not considered ready for EOV status by the OOPC, but the GOOSE task team is preparing a more detailed proposal on this ocean mixing. And bottom fluxes are still under development and probably not ready for measurement. Temperature and salinity are important physics EOVs, and they have been measured by ocean sites for a very long time. More measurements are needed to improve and evolve climate models mainly for improving deep mixing parameterizations. Bob Weller who's been working very hard on this, points out that we need to resolve the aliasing of higher frequency variability that occurs with GOES ships' 5 to 10 year measurements, and even with Deep Argo's 10-day measurements. There's a phenomenon, basin wobble, that occurs with some of these measurements. And ocean sites' deep temperature and salinity sampling every 5 minutes over many years can help school us about the temporal variability of the deep ocean with regards to temperature and salinity, as well as help resolve some of the technical challenges of deep observing. Seabird 37 lessons have revealed compressibility of components in the conductivity sensors, with drift occurring for many months as it asymptotes to a single value. There's also problems with sediment deposition on deep conductivity sensors that cause calibration problems, and this is exacerbated by the fact that sediments washed off the sensors on recovery. Intercomparisons and parallel sensing is crucial, and Bob gives an example of the Roots mooring site that has overlapping deployments of temperature and salinity sensors that are near the Aloha Cabled Observatory, and this has proved very useful in learning about temperature and salinity variability. I've been asked by Bruce Howe to mention the SMART cable endeavor, which he hopes can become part of ocean sites. SMART cables are a game-changing, innovative technology that many hope to be implemented as part of the Decade for Ocean Sciences. There are projects underway now in Sicily, Vanuatu, Indonesia, Portugal, and elsewhere that involve the addition of repeaters to existing deep-sea cables. They would represent a first-order addition to ocean Earth observing systems and would inform on tsunamis, earthquakes, climate, sea level, and much, much more. The biogeochemistry panel is led by Felix Janssen, and they have identified a series of EOVs that they believe ocean sites can help with. The first involves export flux measurements, and they propose that additions to ocean sites moorings could include sediment traps and imaging devices that monitor particle fluxes. They also believe collections could facilitate molecular, elemental, and isotopic composition analyses of water and particle samples. To advance benthic organic matter cycling and our understanding of this, they propose that sediment sampling and deployment of respiration landers could occur during ocean sites maintenance cruises. Similarly, deployment of simple time-lapse camera landers could occur for year-round benthic imaging, or deployment of benthic crawlers with imaging and flux measuring devices. And then a third, EOV, the greenhouse gas measurements, particularly for nitrous oxide and methane, are important and need to be advanced in the ocean interior. This could be done by upgrading ocean sites moorings with gas sensors in the upper mesopelagic, and this is particularly important in outflow areas of the Arctic and the eastern boundary upwelling ecosystems. These would complement hydrographic sections and other measurements that could be made with volunteer ships. The BioEco panel is led by Henry Rule. This panel has been working to develop clear examples of work outflows that can harmonize BioEco EOV work across ocean sites partners, and they've been working in particular with the EMSO Science Services. Henry's been working on a workflow for invertebrate biomass, which is shown here, lots of detail. This panel also advances ocean best practices and delivery to specific stakeholders. Some of them you can see listed here. And there is a suggestion that new BioEco capability could be advanced by ocean sites by including biological sampling on ocean sites moorings. These might include camera and imaging systems for plankton and megafauna, past acoustic monitoring to advance the ocean sound EOV, and in situ genetic sample preservation and processing. DEUCE hopes to advance the EOV observation and the integration through a series of 3 demonstration projects. These would demonstrate the feasibility of integrated and coordinated deep ocean observing in its broadest sense. It would tie together not only the measurement of essential ocean EOVs, but it would bring together separate but existing but separate deep observing programs and communities, test new technologies, demonstrate the benefit of these deep data for policy management, conservation, and the private sector, and work on data integration. And our 3 areas of interest are the Azores region here, the Clarion-Clipperton zone off of Mexico in the East Pacific, and also the Northeast Pacific, where the OI and ONC observatories are. We're very interested in knowing what ocean sites assets are present in these areas and who the contacts might be for these assets. And finally, I'd like to just discuss briefly what we believe DEUCE can offer ocean sites from the data perspective. DEUCE is a forum for coordinating across observatory types, programs, scientific endeavors and disciplines and countries to identify and endorse ocean best practices and share and leverage technologies. DEUCE can help advance findability, accessibility, interoperability, and reusability of deep ocean data for cross-program data discovery and access. We believe DEUCE can help ocean sites data be found and used in the context of other deep ocean data, supporting overall greater use and impact. DEUCE provides a framework for bringing together deep ocean scientists and data facilities with policy and management, with the goal of moving data through to societal impact. And DEUCE provides a forum for groups to coordinate and move forward together. It's important to recognize we're not building a new interoperable system that's going to sit on top of or compete with other efforts. We really want to bring together and help coordinate the existing programs. I'd like to close with a series of questions that DEWS has for ocean sites and that can also help lead our discussions. How is Ocean Sites interacting with Goose? We'd like to know that. How does Ocean Sites help shape EOV requirements for the deep ocean in particular? How does Ocean Sites interact with modeling efforts? And then finally, how can we promote Ocean Sites Goose interactions? And with that, I'd like to thank you for listening.